this talk is more than a talk because it's 1 hour and 15 minutes. I try to make a uniform talk that has a sense. It's more on use, on how to use these methods. Most of the methods have been introduced already: deep learning and molecular simulations and so on. Molecular simulation not so much, but there are some slides here about molecular simulation, what it is. So then, well, stop me because there are many topics. Stop me if you need clarification on something, because I might overlook some stuff. So the title is "Drugs as a Niche Environment." So hopefully will become clear by the end or during the talk. And so there's supposed to be slides here. Here. So just a couple of slides on drug discovery if you really don't know anything about it, and a couple of means just really two. So it's just a difficult process because it's time and resource consuming. There are many molecules that could potentially be a drug, but it's difficult to find it. They need to have all the correct properties and so on and so forth. So it ends up being a very expensive, both in money and in time, for a pharma company to get from all these mass of molecules. Let's say that after they do a first screening would be maybe start with 10,000 and so on, and then they go down, and then you take many years to get to the available drug. And so it is a relevant problem from an industrial and practical point of view. And the way that from what it matters to us is also a very complicated problem. Sometimes I say that it's not a problem, in the sense that it's many problems all together. There's not a single solution that would fit it on. But from a physical chemistry perspective, you could think of it as you need to find some molecule, some chemical material that fits like a key in some protein pocket, and then this alters the functions of the protein pocket. So from what it matters here, we're only interested in this sub-aspect of the drug discovery process, which is how the molecule, what's interaction between the molecule and the target, and properties of the molecules, and so on and so forth. So what's the machine learning, and that because you probably keep receiving mailing like this, like I do, it's probably good to have a definition. Hi Gianni, apparently I is solution to everything. So we need to, it would be good, this is just an invitation to a conference, but these kind of sentences are these days unfortunately quite common. So what the hell do we mean by AI and machine learning in this context? And so what is artificial intelligence drug discovery, and what does it mean? And a question that might be, it wasn't obvious to me, is what is intelligence even? And actually there are lots of discussion on what is intelligence. What does it mean to be intelligent? And one definition that I really liked was from Ronnie Brooks, which corresponds to the behavioral intelligence kind of field. That is, intelligence is in the eye of the observer. So it's not a property of what we claim we call intelligent, but it's actually an emergent behavior that an observer from outside, who doesn't understand the rules by which something is moving, and because he doesn't understand, he says intelligent. If you look at a Roomba, is the guy that made Roombas, the cleaning, it might look like it's an intelligent behavior because he goes around and he has a very complex behavior, but it's actually, on a basic level, it's just a combination of two rules. I like the walls, I don't like to eat something. And just this makes a kind of complex behavior that is following rules and avoiding obstacles. And there are other kind of example where with very simple rules you can have a very complicated behavior that might look intelligent from the outside. Another more recent definition is intelligence measures is a measure of an agent's ability to achieve goals in a wide range of environment. And this is definition that is based for DeepMind. Craig Legg is one of the founders of DeepMind. So they try to, and that's why you see that they're applying machine learning to many different environments and trying to make it general. And there is also a much more practical definition is I just want to replicate human level behavior or human level intelligence. So if I'm applied to a task with some sort of machine, I like the machine to be as good as the human or the expert human. This, for instance, is LeCun likes this. So for him, artificial intelligence means kind of having something that is like the human. Doesn't mean that the human is intelligent, but is. And there is also just a synonym of machine learning, which is actually the most common solution. So we'll use it not as a synonym of machine learning, maybe as human level intelligence. So it's our baseline for what we would like to achieve. So drug discovery was like to convince you it's a good niche environment for human level intelligence. So if we are here to develop human intelligence or artificial intelligence, you could have something that drives a car or does many things, but drug discovery is a good restricted environment on which you can apply this. And because it's difficult, because it's important, and because there are lots of tools that one can use. So what are the elements here? So there are observables, which are this observable not in the physical terms, observable in the reinforcement learning terms. So there are things which are get given to an agent, and in this case a kind of molecule, proteins, and so on. There is an environment, which is nature, so you need to make experiments and to see the properties of these molecules. And there is an agent, which is a medchem team, usually in a pharma and a biotech, which tries to be as clever as possible, as rational as possible, in order to get to this drug as quickly as possible and to the best drug. And then there is a reward function, which in this case would be find a cure, but it could be more specific, like I want a molecule with these properties, and giving a set of properties. So these are actually the definition of reinforcement learning entities, and because the query in the environment is expensive, you have to synthesize a molecule, you have to test it, you have to do a bioassay, and so on and so forth, and also the medchem team in pharma is expensive. That is where you want to work. So you want to practically create computer models and programs, computer models for the environment, so computational model that predicts the properties of your molecules, and also programs which act as the agent and replace the CompChem or helps the CompChem. This could be a vision of what that means. So you have a platform, you take a protein from the PDB, and there is, in this case, there is a ligand, and you start to test automatically many ligands. This is using programs that we have. In this case, we test several properties of these ligands, and then this is taken. You can probably read from there, but it's taken from zinc. Then is docking these things. So it's finding active, inactive, and so on. In this case, is from the one is selected as active is measuring activity, is predicting activity, trying to predict activity of what's the best candidate. Then it will try to do some physical simulations of these things to really check it out, and so on and so forth. So if you, in this case, you have some sort of program which uses predictors and regressors and classifiers and so on in order as a model of the environment in order to iterate this process and use a simulation. It's just a possible path that you can take. I mean, you can have way more complex things. Okay, so how do we apply machine learning to this environment? And the normal way is, and the classical way is, you have an input molecule, you extract some features, could be fingerprints, descriptors, and so on, and you create a predictive model which predicts you something, and could be log P, could be affinity, could be any other property that you're interested in for your ligand. And in the deep learning waves of application, in this case, you kind of eliminate this part more or less. So you have a molecule, you can have a graph or 3D representation. So you have some sort of representation, and then you try to learn the transformation that gets you to the prediction. In theory, there is less domain knowledge in this way and more compute power. And we've been working a little bit in both, and I'll show you a little bit what is the conclusion we can extract so far. So, we started several years ago with to kind of build predictor and classifier to create the model of the environment, the model of nature that we needed to have to have a drug discovery gym, again in the reinforcement learning sense. So we have BindScope, which is an active-inactive classifier, KDIP, which is an affinity predictor or scoring function, LickVoxel, which helps in generating spatial pocket properties to know which molecule would fit into a pocket, and LickDream, which is a generative model for that given ligand shape will give you multiple smiles which are compatible with this shape. So these are two generative models. In this case, starting from the protein pocket. So I'll go quickly through these cases, and just to give you an idea of what can be done. So we started, as I said, 4 years ago. And so what we decided to do was to exploit everything that has been done for machine vision. So be as close as possible to machine vision. And the closest thing we could do in images, you have 2D representation with 3 channels. And in a protein for us was a 3D matrix with multiple channels corresponding to the physical chemistry property. There are other ways to do that, but when we started to do this, was actually, I remember, was like ACS in San Diego, and there was, if you would put deep learning in ACS, there were only 2 talks, ours and another, and Atomwise, and it's and actually independently we got this kind of representation. Then also COS use the same representation or similar representation, visual representation. It's actually not a very good representation because it's not rotational invariant, so you're actually in a non-translational invariant, but it's what we used back then. And as I said, the way it works, you take all the atoms of your protein and then you can divide it by channel, like for instance hydrophobic or aromatic and so on and so forth. And then for every atom you build a kind of occupancy kind of around the atom, so you can interpolate the atom on its size. You interpolate the atom position on a grid. We usually use grid of 1 Armstrong atom, and so you get figures like this, one for each channel. We have 8 channels for the protein and 8 channels for the ligand. So in images you have 3 by whatever, 84 by 84 for Atari games, and in here we have 8 by 16 by 16 by 16. And what we do, the same that we do in ImageNet, this 16 by 16 we crop it. So if we have to analyze a protein which does not fit in 16 Armstrong, we just take subsample of this area. And okay, so we created a bunch of applications, and also all the applications are in this are freely available on this website, which is called playmolecule.org. So you can test them or use them. And DeepSight is the first one we did, and DeepSight, I mean, they're all based on neural network. Like I said, 8 by DC16 and 16. There is standard convolutional layer and so on and so forth. I'm just trying to tell you what they do, what can be done. So in this case, this application, DeepSight, predicts binding site. So where a molecule could bind inside on a protein surface, so you could target that pocket. And not every pocket is as good. So there are pockets which are good, the pockets are not good. The way that this was trained by taking all the crystal structure where there was a ligand and say, okay, here there is a ligand, and here in these other parts there are no ligands, and so it's a simple predictor this way. And with a basic network, we never made too much attention on the network. We always pick whatever similar to kind of a vision network, but without optimizing it too much, nor for hyperparameter, nor for anything. Immediately you get to performance which are similar or slightly better than the state of the art at that point, but similar, not completely, not substantially better. It gets there very quickly, no? And I mean, this one of the best programs to do this, it was called FPocket, and probably it was developed over many years. We just came there and it worked. And I think this is the main advantage, actually, of the method so far, that it's transferable in the sense that the human is transferable. It's very easy to pass from one problem to another problem and get very good results very quickly, but not necessarily better not necessarily substantially better than what else is there. Another one which attracted some attention is KDeep, which is an absolute binding affinity predictor. So you pass the protein, the ligand, you voxelize, you create this thing, and then you predict the affinity. And the interesting bit, I guess, is that it gets to the same performance of, in theory, exact method like free energy perturbation method in molecular simulation. Of course, because the force field is not very good, but this is kind of instantaneous compared to having to create a simulation for that. Bind scope is the same kind of thing, but it will just tell you if.
The previous one with the experimental.
Yeah, it's always we take PDB bind, which is a database, which has we are all structure based because we weren't really looking to do QSAR. We really weren't looking to do really a drug discovery thing. We wanted to have some some relationship with chemistry or whatever is there, hoping to generalize. So the initial idea was, can we learn chemistry? Can we have can we really generalize between pocket and so on and so forth? And so we take PDB-bind, this protein. There is a database which has the structure of the protein, the ligand, and the affinity of the interaction. Okay, yeah?
So are you averaging or different ligands, or just taking any ligand?
We take any ligand which has a binding affinity. And you take the pocket, you take around the link.
But the network only finds pockets to bind some ligand, or for a specific ligand?
Now, this just tells you, if you give a ligand bound, any ligand bound will tell you what's the predicted affinity. And it does that because it's been trained in a regression, supervisedly, saying, okay, this in this pocket, the protein ligand, and this is the affinity. This other pocket, protein ligand, this is the affinity. And it's very simple thing, but it reaches the performance of, in theory, exact method in MD. So it's bad for MD more than good for this one. And
so does the network given the information what is the protein and what is the ligand?
We use 16 channel. Yes, we use 16 channel for when there is protein ligand. There is 8 channel for the protein and 8 channel for the ligand. So another thing that is common in drug discovery is lead optimization. Lead optimization, while KDeep is like you can pass any protein and any ligand, and it will tell you an affinity. But if you have two ligands which are homologous, so they come from the same series in a lead optimization phase. In a lead optimization phase, you have a scaffold of a molecule which is more or less the same, and you change little atoms of residuals around in order to optimize some properties. In this case, the affinity between the two are not so difficult, not so different sometimes, often, and also the difference between the molecules are not that much. So you could predict it as predicting 2 points in absolute binding affinity, but you could also just ask what's the difference between the two. So if I replace the ligand with ours, which is called delta binding affinity, and these are kind of examples of what you get. In this case, we used BindingDB as a database, and this work was done with also KDeep, like I said, this year. And we had to do something maybe a little bit different from the network, in the sense that the network was convolutional, but you had to pass one ligand, the other ligand, protein ligand, and then you want a number. But you also want that the number, when you invert the order of the ligands, should becomes minus the number. So we create a symmetry in the network in a way that these two lobes are the same, and then we just do this minus this when we go here, so that these properties are automatically true. And again, compared to FEP, we are the same the same speed. Let me explain you the same speed, no, the same performance. Let me explain you the plot. Let's say this one. So this is a target, and for this target, you have a set of ligands, which is in a congeneric series, and you want to predict the ranking, the Pearson between this one. And so this is the Pearson, and what we do when we train this, we do this. Okay, we have a pre-trained network, and then we apply this pre-trained network to predict all the ligands, like if we don't know anything else about the protein. And we don't do very well, so we do 0.4 or something like this. And then we say, okay, now we have on top of the crystal structure, we assume that we know one of the ligand of the series. and then we can already compute 1 delta, because we have the crystal and we have the data. This is the case with 1 here. And it's already improving just by adding 1 point. So we retrain the network by adding this extra point, starting from our prior, if you want. And this, if we add the 2 ligands to the one we know, and 3 ligands and 4 ligands. Now with already 5 ligands, we get the performance of FEP. And
how many ligands are in the series?
From well, normally enough, when the drug discovery process is finished, is hundreds of thousands. So they don't care absolutely, and they do few per weeks, 10, 15 per weeks anyway. So that's totally not a problem for a pharma company that you need to retrain. So okay, so we pass this. We collaborate with several pharma company, and we pass this code to Janssen, to Pfizer, and to Biogen. And they tested. They had the code. We didn't have the data. And our code never seen their data more than once. So it was trained by us, then it's retrained on their series, but there was no interaction and say, okay, it doesn't work, let me see. No, it was given, they tested it, and they reported the performance. And this is the GLIDE score, which is a docking score, and we beat it badly in all cases, apart from one, where we are kind of the same. And so practically they don't have any tool which performs like this. And it's really valuable to know, to be able to predict which ligand they need to synthesize and which one they don't. The same for Pfizer and for Biogen. One thing that we tried to do is, so we had, in the case of Janssen, the data was on, Janssen actually came there, came to the lab, so we could apply it in a time frame. So for each ligand we had the time at which was synthesized. So we started to do this kind of simulation. So we start from the first molecule, and we take the 10 closest to that in terms of fingerprints or something, and then we rank them based on the algorithm, and then we pretend that we synthesize them. Now we have the affinity of those. We retrain the model on that affinity, on the affinity of those, and then we take the 10 closest to all these, to the best one of this one, and so on and so forth. And the goal was to see how many molecules we have to synthesize compared to the real world to get the most potent ligand that they had. And here, depending on the cases, here we gain between factor 6 sometimes, so you have to synthesize 6 times less molecule. This is of course still a simulation done afterwards, but it was just to have an idea. Okay, so this predictor and classifier were mainly to create this model of the environment. We want to ask nature as little as possible because it's expensive, it's very slow. And so if we had very good models, that would be ideal. Another thing that looked promising was, okay, if we have 10 to the 60 molecules that we are interested at, and that we cannot screen them, we cannot filter them, because we cannot even enumerate them. We cannot do anything computationally with 10 to the 60. And so the only solution where to kind of fish in this space was to use imagination. And generative models are doing this. So they generate from a distribution which is attached to some prior. And so the idea was that let's use generative models to generate molecules starting from pockets or other molecules. And what we really wanted to achieve was that, given the pocket, we really wanted to generate 3D structure. but we couldn't do that. And the reason why we couldn't do that because was even using GANs, the shapes. I mean, you can see the kind of a ring here, but in other cases it's unclear. I mean, you still have lots of molecules that would fit, would be compatible with this configuration and with a lot of errors. So what we ended up doing was kind of a bit simpler. So we first, for instance, in this case, in case of Leak Dream, which is the generative model, we start from a seed molecule, we shape it, we create a lot of conformers, we create the shapes, the voxelization, and which in this case is this one, and then from the shape we do captioning. So I think Frank spoke a little bit about captioning. So from the image you can generate text, and from the image you can generate smiles. It's actually the same kind of procedure. It's not very good. It was just the only way we could think of. There might be other ways, but is what we've done. So we could go from a seed molecule to generate other molecules in a generative way. And the network is very complicated for the many components that there are. But it allows to kind of, in particular, it's generative in two ways: in generative in the autoencoder part, in the variational autoencoder part, and also in the captioning. So even the captioning can change. Okay, so in the case of Leak Dream, we use a variational autoencoder, and the problem with the variational autoencoders is that it tends to generate blurred images. So we use, in Ligan, we use a GAN to generate the shapes. So given the pocket, there is a GAN that provides shapes, and then again we use the captioning to so it's kind of the same as the other one, but instead of using variational autoencoder, we use a GAN to generate the shape. And this worked a little bit better. We compared to, but again, not substantially better. Like in the top, I think was the top 10%, I think, was kind of a factor 2 better than random. So you could, if we generate molecule from this, and we compare it with what with just random molecule, we were 2 times more likely to get to the right active molecule than random, which is not a lot. So okay, so how good are these methods? And what time did they start? 3:45. Okay. So how good are these methods? So we like challenges, so blind challenges. I think it's really important to do these things. And we applied to the D3R challenge, which is an international competition for computer-aided drug discovery tasks. And there were multiple challenges, like blind prediction of binding modeling at affinity, and so on and so forth. And also we applied to the sample 6 challenge, which is log B prediction. And well, to make it short, with KDeep we managed to get first in the binding affinity and the post prediction. But very bad with the same method, very bad in others. So it's not totally crap. Sometimes it's good, but it's not totally good. Sometimes it's crap. So it could have been always bad or always good also. So there is still there's still cases that doesn't work, but there are cases where it works very well. Probably because it doesn't generalize very well at all. and it could be for many reasons, even the featureization. I think the log P prediction is interesting. So we applied with multiple models. We applied with a fingerprint-based XGBoost, which is actually this one. So we write second practically the same LMC and MILE than the first one. And we apply with graph models. And so more deep, more nicer one in theory. So a graph convolutional model for the ligand, which actually goes down here, went down here. So which is still close, but a lot higher. And we actually went to Biogen last year, and the challenge was trying to improve on their methods for several predictors they had, and they always used fingerprints and XGBoost, and we couldn't practically. So the only way to improve their method was to use XGBoost and a neural network and just average several models, but then the improvement was minimal. So I think this ends this part, but so the point so far is this one. So this method, they kind of work, but we don't see that they are substantially better than previous methods. In particular, if you use Morgan fingerprints, they are crap. But if you use things like physical properties that you can fingerprints, which you can get from RDKit easily, that's a lot of information to give. So a graph convolution method should learn that pattern is as important for ionizations and so on and so forth. So we find that actually the physical chemistry fingerprints are really important, because it practically are using physics to tell what the properties of this molecule, and this property can be very highly correlated with hydrophobicity, for instance, of the product. So it's with the data that there is, I don't think there is enough data to learn these features automatically, and there is very little data in these things. And even if you go to pharma, the data is very non-uniform. So they have series, and they have lots of data around the series, but they have nothing outside. So it's even if they are 100,000 points instead of 5,000 points, but these points are really skewed in a way. Okay, so this ends this work that we did over several years. And actually, another work that we did for a long time was we worked in molecular dynamics for a while. Well, still the idea is to do a predictor and so on and so forth. And in this case, physics is the model. So provided that the force field is good, this would be good. There is nobody would do machine learning in plane design, airplane design, because Navier-Stokes is nice. It's nice in the sense that it's exact. It's only momentum, energy, and mass conservation. So there's nothing wrong there. And so that's why I think this machine learning potential for quantum are going to be very important, because if we manage to move the quantum machine learning level to a level of speed which is decent, doesn't have to be as fast as classical, but decent, then there's no point to do the machine learning. I mean, you just do the physics and compute the same way that you do it with hydrodynamics. So classical is very fast. These days is 1 microsecond per day. You can generate 1 microsecond of data per day for a small protein, largely thanks to GPU. And so you have the option to launch many simulations, and you want to launch the simulation in a possible optimal way, and decide where to launch the simulation. And for instance, you could start here. These are initial position in initial configuration of a simulation. You run them, and they go over here. This is the kind of effective potential that is underlying this system that we're running. And or you could be a little bit more clever and say, well, I start from here, run here, but then the next time I run, I actually run from here. And then from here I can explore way more. And this, because we have all the machinery of Markov state model to rebuild the equilibrium distribution from the local equilibrium distribution, it doesn't matter where you start to a large extent. It doesn't matter where you start, so you can just start wherever you want, wherever is optimal for you, based on some criteria, and then build up, projects this simulation in Tika space, cluster them, build the Malcolm model, and then reconstruct the dynamics. And this we've been done for quite some years. And this is an example of, so this kind of procedure is called adaptive sampling. And it's unbiased, so you don't need to modify the Hamiltonian. The Hamiltonian stays the same. You just decide at every step where to restart your simulation. Like, for instance, you start from these blue ones, and then you restart from this one, but you don't restart from these ones, and then you restart mainly from here, and then mainly from here, and then mainly from here. So it creates kind of a tree of restarting conditions. Now, there are several papers that have been working on this. And I think all these papers suffer from, there are unclear convergent properties. It's unclear what we are doing. It's just a little bit heuristic, everything. Sometimes anti-intuitive. For instance, we show that for trypsin benzamidine, the best was to select things which were in the metastable state, which seems strange because you want to select things which are outside of the metastable state to sample better. And so I never understood that until recently. Why in a real system is better to restart from metastable states instead of restarting from other places. It's against the interest of adaptive, no? So to restart from metastable state, I just run the simulation. I would already be in the metastable state. But actually there is a slight difference which makes the difference. And so this process of this process of selecting things, there is an agent, there is an environment, there is a reward which you can define, and so it becomes a Markov decision process which you can treat it like that. And so I just quickly introduce you with Markov decision process. The goal is to select some action, in this case where to restart my simulation, in a way to maximize some future rewards. What is the future rewards? We need to decide. It can be reward, might be delayed, and so on and so forth. The Markov process, the Markov process is the Markov process that we use all the time. So we have a finite state of states, S, and we have a transition probability matrix, which tells us where we go from state S, and we're probabilistic where we go from state S to state S plus 1. In a Markov reward process, you add a reward function and a GAN discount. So it's a Markov process where you add a reward function. So you have this reward function is kind of an average. So given a state, it will give you a reward. Will give you a number. And then a discount factor is used mainly for convergent properties. You like to have a finite horizon where you sum these rewards, or you put gamma some numbers, and then this has nice convergent properties. So you guarantee that that they find a solution. And so if you define all of this, you can define also the average of this cumulative reward, starting from state S. And this is called the value function. and it is practically the value that you can reach in the future starting from that state. And there is this equation which is fundamental in reinforcement learning and fundamental in micro-decision process, which is the Bellman equations, which allows you to compute the value function in terms of the value function. So you can demonstrate that the value function is the average of the instantaneous rewards at t+1 plus gamma for the value function at t+1, at the state of t+1. And this, by just iterating this, you can solve the value function. So finally we can introduce the Markov decision process. So Markov decision process has a finite state of states, and now you add a finite set of actions. So the action in our case would be where to start the simulation from. And yes, probability. Has a state transition probability matrix, so which does not have to be known, which given an action and given a state, it gives you a state s+1. And also a reward function, which given a state and given an action, it gives you an instantaneous reward. So what we added is the action. And this is the common things that you have in reinforcement learning. So you have an agent, in this case is my program, which decide what simulation to restart the simulations, obtain some rewards that we will define what they are, and some other states which will define what they are, and then goes back to the agents to define when the simulations are over, to decide where to respond more. So what we have to do here is, in this context of adaptive learning, what are these elements? And there's not a single solution for this. You could decide different things. So what you really want to know is the optimal policy practically. So a policy is a distribution of an action given the state. So given my current state, what is the best action in the sense that to maximize the reward. Okay. There are two things you can do with this setting. You can predict. So in the case that you know the jump process, you can evaluate given a policy, you can evaluate the value function over the policy, and then you know everything, what's the best state and so on and so forth. What's the value of each state for that policy. Or you can solve the Markov decision process, which means find the optimal policy. So these are the two things that you might want to do. Either predict, so given that I know the model, I will just predict what's the value here and what's the value there, or find the optimal policy, which is solving the policy. For instance, in the case of playing Go, the idea was to find the optimal policy. What's the optimal game strategy there? Okay, so how this applies to molecular simulations? A simplification of the Markov decision process is called the multi-arm Bandit problem, where practically it's a Markov decision process where the states are the empty state. And so you have only the action space, you have the reward functions, and in this case we can have k actions. The R is the unknown probability distributions of the rewards, and then each time steps the agents applies a policy given the actions. There is no state, so the policy only depends on the actions, which comes from a probability. And the goal is to find the optimal policy that maximizes the cumulative reward. So this is the definition of the multi-arm bandit. So in the case of adaptive sampling, what are these elements? So adaptive sampling works by performing several epochs of short parallel simulations, selecting information from what to explore in new simulations. So the action set is kind of the history of all the confirmation that I saved for the data that I have at that current time. Okay, so every every conformation that I run and I save, then I can restart from those. And the reward function can be anything. We decided to connect it to, because we can build a Markov state model of the current data that we have, we decided to connect it to the free energy of each state, such that you want to maximize the minus free energy bracket. And so you get more reward if you find state with lower free energy. And there are known methods for solving the MDP. One method is called upper confidence bounds, which is has better theoretical bound than epsilon greedy, which is what we usually used before. And in this case, we used so you have a value function, which is QDPi of the actions, which we defined, and then you pick the next action based on this value function, then the logarithm of the number of steps that you perform, and the number of samples that you have for a given action on that step. So you're given this, you pick given this formula, and this guarantees you that you find an optimal policy. Another thing that was common in adaptive sampling was, okay, let's say that I have some experimental information of my system, and I want to use that. So let's say I might have contacts for a protein folding case. So I want to sample, but I want to use this information that these two residues should be close. And the way that the way that it was done before is that was simply imposed. So there was these two residues close are favored. So every time I see a conformation with two residues close, those are sampled more. And this is okay if the data is correct, but it's not always correct. So in the case that, for instance, one data point was wrong, two contacts were supposed to be close, but they weren't close, then all your simulation would be would be favoring this conformation, even if the MD says no, this is not the case, this is not the case, this is not the case. It will keep doing that because your algorithm is blind to that. So, but in a Bandit context, it's easy to do to start. It's easy to do an off-policy initialization. So the way that you say that you have contacts, and for instance, you're doing protein folding simulation, the way to say I want to favor these contacts is that you set up a policy which favors that contacts, but then the policy gets updated by the model, by the algorithm. So if that assumption was wrong, this with time, the MD wins. So the statistical data that you have wins against your initial prior. So you can decide how much you weight the prior and how long it will take to forget your prior. And this is the way that we implemented in, well, we call it now adaptive Bandit, not adaptive UCB, because UCB is only an option, a possible option. And so what happened then? So let's say we have something like this. So this is a 2D potential. So like here we're running Langevin dynamics on the 2D potential. So you start MD simulation, you collect the data, you cluster the data like you see here. You create a Markov model, you rank the Markov model, you just compute the free energy, you update the Q, you pick the white, which was the based on UCB the best restarting simulations, and you go on. Yeah?
Question, I'm a bit confused. You said that you use a Bandit algorithm, but Bandit assume that each of them has a distribution that actually doesn't change in time. This may not be true for your case.
it's even worse than that, because it's the reward function is fixed in a Bandit, while here I'm
Your reward function changes.
yes, it's changing because I'm estimating it. It's not given by the environment in a sense, because I don't know it.
No, it's given by your previous your history.
Yes, it's given by a Markov model built on the history. So it's not even a question of independence. It might even be changing and so on. And so we defined 3 potentials, and but actually then we started only 2. And the reason was that there is kind of an optimal way to explore in adaptive sampling, which is just sampling proportionate to 1 over the number of samples that you have for a given cluster, and that is one of our baseline that we use. And then I've also created this funnel potential over here, which the idea was actually it wasn't to mimic protein folding. It was to I'll tell you later why we decided to use this case. So in this case, so we have random sampling, we have low count sampling, which is this explorative optimal way to sample, and we have the adaptive UCB case. And in this case, the equilibrium is this, the real equilibrium is this black line, and we try to see how much time each algorithm needs in order to get there. And apart from random, both low counts and adaptive UCB works the same. So it doesn't work any better than random. And that's actually why we decided to generate this other case, because I was thinking why it works as good as random, and is that if the explorative policy is the optimal, and it is here because you just want to go over this barrier. So the more you explore, at some point you will fall on the other side and then go and find the other barrier, the other pocket, the other well. So it's kind of impossible to beat an explorative algorithm here. And but in this case, in the case of the wells, if you start here, then and you just explore, because the inner barrier is smaller has less space than the outer barrier, you're more likely to go out than to go in. So in an explorative algorithm starting from here, you're more likely to explore out simply because the barrier is wider there and than in. And so it's less likely to go to the center, which is where the minimum is. And indeed, in this case, the adaptive UCB works a lot better than low count and than random. So it's practically depend. So your adaptive. This was also shown by Bowman, Greg Bowman, who's another guy that works on adaptive sampling. It kind of depends on the underlying potential that you have. If your molecular system has this potential or has the other potential, one algorithm can be better than the other. So it depends a lot on how nature is done. And another thing that's to show you what I told you in this case, we have a prior which tells that is from so it's like this, so it's kind of a slope. So and we start once from here, and once we will write to reach the other well. Now, because this is against the slope, so practically we're telling to these simulations, your binding pocket is on the other side, because we're giving a prior which is going down. So it would need to overcome our wrong experimental information in order to find the pocket. And here we give it, no, this we start from here and we have to get here. In this case, the information is correct. The initial information is correct, and because it's in the right direction. And what happened is what we expect, so that actually adaptive UCB works slightly better even in the case that the goal is correct, so that the direction, the experimental direction was the right one, to where to find the other well. It works a lot better when the goal is opposite to the reality. And this you can make it as bad as possible for the others, because you can just make the goal more and more strong, and they will never sample the rest practically. And this shows the, like, for instance, epsilon greedy with the wrong goal practically never goes to the red point, never even sample it. In the case of, in a more complex case, like in case of billing, so this we project on 2 ticket dimension. The way we generate the 2 ticket dimension, we have the entire data set. We just create the 2 slower dimension, and we keep that fixed. So we have the transformation fixed, so that we can project on a fixed plane. And then we do the crystal structure is down here, the misfold is in here, random coil is here, and again we give the wrong. We compare the several algorithms, the different algorithms, and with adaptive UCB we do find the crystals, but with the case of fast, for instance, we don't, which is another type of algorithm. So that's more or less what I wanted to tell you. So I think the main point is, so the global idea was to learn chemistry. So can we learn chemistry, and I guess that doesn't work very well, but in the sense that it doesn't generalize, but we use in very simple voxelizations. So we're now trying to use SNET as a Fisherizer and so on and so forth, so to be more to be able to generalize better these properties. I think there's a lack of data, which is problematic and kind of hard to solve. So if you don't have that data, a very simple method like random forest would and fingerprints would give a very hard baseline, because you're providing a lot of information to the random forest through this fingerprint, a lot of physics through this vectorization. And for generative models, I don't even know if it works, because we couldn't test it with pharma, because practically no pharma was interested in synthesizing something which was outside of a molecule which would probably be active. So if they have a molecule which is active, and even if for a blocked project, so they cannot go on that project. You say, well, I have this series of different models created by some super generator, and because they need to understand how do they synthesize that, how they buy the scaffold, so they need to understand all the synthesis process for every single one. They will not do that process unless they're very sure that molecule has some activity. So it's kind of a dead end, if you want, because if they can't move out of that situation, it's hard to. For the MD, I think there are there's still the same 2 problems. One is sampling, and I think this method might help. Even if they're not like theoretically exact, because we have to adapt a little bit to to the case. They're a lot better in terms of understanding what are the parts that we're using. And then hopefully, I hope that the quantum machine learning will kind of change drastically the situations of the force field. They're not that bad, the force field, but they don't guarantee you the correct answer. So if it was, if in a month of calculation on 100 GPUs, I would have some guarantee that I have some crystal pose of the ligand that I'm care of with the protein. Pharma company would do that if it was okay. Instead, while the crystallographer was dry, I will just put that on. But if then when you come out after a month, it's not clear, and then there is also all the problems of the initialization, which we tried to solve. We created a lot of tools in Play Molecule to help in setting up the molecule. A lot of errors are not even the force field, there's a lot of human expertise which are required in order to set up the simulation the correct way. The protonation of the protein, the protonation of the ligand, the parameterization of the ligand, and so on, so on, the condition on which you run. And a stupid example is once we equilibrated, we want to do the protein folding, and for a disordered protein, we broke up the protein by the protein that we have, the NMR we added the protein using 500 degrees. There was a proline there, the proline flipped, and it stayed flipped for the entire simulation. So we had to throw away the entire simulation. So there are all these little things which are as problematic as the force field and the sampling. Okay, that's all.